To understand the physical limits of modern computing, we must examine mathematical structures that grow so rapidly they eventually collapse under their own weight. The classical Fermat number formula is a double exponential. F sub n equals 2 to the power of 2 to the n plus 1. At low ranks, the outputs are manageable. Rank 1 is 5 and rank 2 is 17. But because the exponent itself scales exponentially, the sequence immediately explodes. By rank 5, the resulting integer is already over 4.2 billion. By rank 10, the calculation hits a physical limit. The required exponentiation generates a number so massive that evaluating it through standard arithmetic exhausts modern processing capacity. This hyper-exponential growth directly confronts the physical boundaries of hardware. We are constrained by the specific architecture of the silicon wafer, which can only execute a finite number of operations per second. At these scales, brute force exponentiation is no longer a viable strategy for cryptography or number theory, as the time required to compute a single rank exceeds the lifespan of the hardware. Solving for giant Fermat numbers is not a matter of raw computing power. It is a structural problem that requires a new geometric approach to the sequence. Index theory, proposed by Zarkouna, suggests that a massive Fermat number is merely the visible surface of a deeper geometric structure. Zarkouna introduces the absolute space, a lower dimensional topology where hyper-exponential growth is flattened. By projecting these numbers into this space, we isolate their polynomial antecedents, the algebraic roots that govern the sequence's growth. The apparent complexity of the Fermat sequence resolves into a predictable underlying mechanical rhythm. The engine of this theory is the continuous generating function, f of n equals 3n plus a corrective term managing rank parity. This fractional component acts as a geometric selector, determining the math based on whether the rank is even or odd. When the rank n is even, the fraction strictly resolves to exactly 2. When the rank is odd, the calculation shifts and strictly resolves to 1. This oscillation acts as a mathematical metronome, regulating the growth of the sequence through a rhythmic pendulum of f of n. This parity selector eliminates the need for conditional logic, baking the geometric rhythm directly into a single unbroken functional equation. Mapping a Fermat number requires 3 topological layers: the antecedent, the index, and the Fermat number itself. First, we apply the generating function f of n to the root antecedent to produce the continuous index. We then apply that same function to the index to reach the final Fermat number. Algebraically, this defines the Fermat number as f of the antecedent. This definition removes the power of 2 exponentiations found in the classical formula, replacing them with a recursive function. Calculating these numbers becomes an exercise in applying a spatial operator rather than scaling astronomical exponents. The entire system grows from a unitary seed, where the antecedent of the second rank is anchored at exactly 1. To jump to an even rank, the system uses a specific quadratic operator, 9x squared plus 8x plus 1. For odd ranks, the pendulum routes the sequence through a different operator, 9x squared plus 14x plus 5. These operators combine to create polynomials where the degree expands to 2 to the power of n minus 2. Because the origin variable x is anchored at 1, the polynomial variables collapse, leaving only the raw structural coefficients. This leads to the theorem of the unitary sum. The value of the antecedent is simply the sum of its polynomial coefficients. This replaces hyper-exponential towers with the addition of coefficient matrices. The computational load is significantly compressed, transforming the sequence into a manageable set of matrix additions. When we analyze the symmetry of these coefficients, we find a specific structural pattern. These constants directly mirror Pascal's triangle. Each coefficient is governed by the reduction formula. M choose m minus k times 9 to the k minus 1 times 7 to the m minus k. Thus, the polynomial structure is simply the binomial expansion of 9x plus 7 to the power of m. The internal structure of any Fermat number is not chaotic. It is bound by predictable combinatorial symmetry. This defines the antecedent through a single equation. By substituting our unitary seed of 1 back into the variable, the inner binomial term simplifies to exactly 16. Expanding 16 into 2 to the 4th power allows us to multiply the exponents. This perfectly resolves to 2 to the power of 2 to the n, matching the classical formula. This framework allows us to map the internal structure of a 20-digit integer like f6 without needing to calculate 2 to the power of 64. The matrice de Fermat, f of n, bypasses the processing limits of traditional arithmetic. By using index theory, we can predict the behavior of these massive numbers, transforming a computational bottleneck into a finalized system of predictable geometry.